Hey everyone, and welcome back to AI.Code.Cast. You know me, always ready to dive into some cool coding challenges. And today, we've got a classic one lined up, combination sum 3. Um, it sounds a bit intimidating maybe, but trust me, it's like a fun little number puzzle. So picture this.
Okay, I'm picturing it.
All right, so we've got a set of numbers, right? Just the good old digits from 1 to 9.
Okay, 1 through 9, got it.
Now, we're also given two special numbers, like uh, clues to our puzzle. We'll call them K and N. K tells us, like, how many numbers we got to pick from our set. N is the target sum we're aiming for.
Okay, like, K could be 3, meaning we pick 3 numbers, and could be, I don't know, let's say 9.
Exactly. So the challenge, the big brain teaser, is to find all the different ways, all the combinations to pick K numbers from our set that add up perfectly to NN.
Okay, I'm following so far. So find groups of K numbers and add up to N.
But of course, there's a twist. We can only use each number once in a combination.
Oh, okay, so no repeats.
Exactly. No sneaky repeats allowed. So, like in our example, with K being 3 and N being 9, our goal is to find all those sets of 3 numbers between 1 and 9 that add up to exactly 9. But remember, no using the same number twice within a set.
Right. So like 1, 2, and 6 would work, right?
Yeah.
Because those add up to 9.
You got it. That's one valid combination. Now, the challenge is to find all of them. And I bet your brain is already starting to think about how to solve this, right?
Yeah.
Like maybe just trying every possible combination.
Yeah, that's what I was thinking. Just list out every possibility.
That's what we call the brute force approach, right? Just try everything.
Right, brute force.
But here's the thing, the brute force method, it's kind of like using a hammer to crack a walnut.
Okay, I can see that.
It works,
Yeah.
but it can get really messy and inefficient, especially when K's start to get bigger.
Right. Imagine having to check, like, I don't know, millions of combinations.
Exactly. It would take forever. So brute force, while it might be tempting, isn't always the best way to go. We need something smarter, something more elegant.
Agreed. So what are some of the, like, pitfalls we gotta avoid? What do we need to be careful about when we're trying to solve this?
That's a great question. So one big one, and it's easy to overlook, is remembering that no repeats rule.
Right. No using the same number twice.
Exactly. It's easy to accidentally create combinations with duplicate numbers if you're not super careful, and then you end up with incorrect solutions.
Okay, so we gotta keep an eye on those duplicates. Anything else?
Another tricky thing is, like, efficiently checking if the sum of a combination actually equals n. We got to do that check a ton of times, so having a really streamlined method for that is key.
Right. We don't want to waste time with inefficient checks.
Exactly. So we need to think strategically, find clever ways to optimize our solution. So we know brute force isn't the best. What's a smarter approach? What kind of tools can we pull out of our coding toolbox?
Well, one technique that often comes up for problems like this is backtracking. Have you ever, gotten lost in a maze?
Oh yeah, definitely. Spent way too much time in those corn mazes as a kid.
Right, so backtracking is kind of like navigating a maze. You try one path, and if it hits a dead end, you back up to your last decision point and try a different path. And in this case, our maze is all those possible number combinations.
Okay, I like that analogy. So how do we apply that backtracking idea to our combination sum problem?
So we could start by picking a number, let's say 1, just like you said before, and then we explore all the combinations that include that number 1.
Okay, so we're kind of building out a tree, like branching out from that initial choice of 1.
Yeah, exactly. And if we hit a dead end, like our sum gets bigger than n, or we accidentally repeat a number, we backtrack. We remove that last number we added and try a different branch.
So we're like systematically exploring those combinations, making sure we don't break the rules, and backtracking whenever we hit a roadblock. Clever.
Exactly. And the really cool part, we can use recursion to make this backtracking logic super elegant. Have you worked with recursion before?
Oh yeah, recursion. That's where a function calls itself, right?
You got it. With recursion, each time that function calls itself, it's like taking another step deeper into our maze of combinations.
Ah, so it's like each recursive call is exploring a different branch of our combination tree. That's neat. And it seems like backtracking would be way more efficient than just blindly trying everything.
Definitely. But there are other approaches too. Have you ever heard of bit manipulation?
Bit manipulation. Yeah, I've heard the term thrown around. It's about using those like binary representations of numbers, right? Ones and zeros.
Exactly. So what if, just hear me out, what if we could represent each combination as a pattern of bits, like a code, where a 1 bit means a number is included and a 0 bit means it's not?
So for our example, with numbers from 1 to 9, Each combination would be like a 9-bit sequence.
You got it. But how does that help us actually find the right combinations, right? That's the key.
Yeah, how do we crack the code, so to speak?
Well, think about it this way. We only care about combinations that have k numbers, right? So we could look at each of these 9-bit sequences and just count up the 1 bits. If it's not equal to k, boom, we can toss it out. We know it's not a valid combination.
Ah, so right off the bat, we can eliminate a ton of possibilities. That's clever. What else can we do with this bit representation?
And here's the cool part. We can actually calculate the sum of the numbers represented by those 1 bits really quickly, right? Each position in that bit sequence, it matches up with a number. So like if the first bit is a 1, that means the number 1 is part of our sum. If the second bit is a 1, then number 2 is included and so on.
Oh, I see. It's like we're using the binary, like the ones and zeros, to our advantage.
Exactly. And computers, they just love working with binary data, so this whole bit manipulation thing, it can be blazing fast.
Yeah, that makes sense. It's funny how a complex sounding solution can actually be more efficient than just like the simple way of doing it.
Sometimes the most elegant solution is the one that digs a little deeper, you know?
Totally. Okay, so we have these two really cool approaches, right? Backtracking, like navigating a maze and bit manipulation, working with those ones and zeros. But what are the pros and cons of each? Like, when would you choose one over the other?
That's a good question. I think backtracking, it's often a bit easier to understand, especially if you're just starting out with algorithms. It kind of just follows the way we naturally think, step by step.
Yeah, it's like how we'd probably solve this problem if we were just doing it on paper.
Exactly. But it can get, computationally expensive, especially when those K and N values start getting really big.
Right, it's like the more branches in our maze, the longer it takes to explore them all.
Precisely. Now, bit manipulation, on the other hand, it can be efficient, but it might take a bit more effort to wrap your head around initially, especially if you're not super familiar with bitwise operations.
Yeah, those bitwise ANDs and ORs, they can be a bit intimidating at first.
True, but once you get the hang of them, they can be really powerful tools.
Wow. So it's all about trade-offs, right? Choosing the right tool for the job based on the specific problem and your own comfort level.
Absolutely. And, sometimes the best way to really understand these solutions is to see them in action.
Yeah.
Like, what if we walked through a simple example, maybe with our backtracking approach, since it's a little easier to visualize?
Yeah, let's do it. Let's bring that backtracking idea to life. So we'll stick with our example of k being 3 and being 9, right? And let's say we have this recursive function. We'll call it find combinations. This function, it's going to take a few things as input. Our current combination, the current sum, and the starting number.
Okay, so we're going to dive into this function step by step. So what's the first thing we got to check inside this function? What's our starting point?
Well, the first thing we got to do is check if we've already found a valid combination, right? We need to ask ourselves two questions. Do we have k numbers in our current combination? And if we do, does the current sum equal n?
Right. Those are like our winning conditions, right? If we hit both of those, boom, we found a solution.
Exactly. We add that winning combination to our list of solutions and move on. But what if we haven't hit that k number mark yet? What if we're still building our combination?
That's where the recursion comes in, right? That's where things get interesting. So we start a loop, and this loop, it's going to go through all the numbers from our starting number all the way up to 9.
Okay, so we're considering each number as a potential addition to our combination.
Right. But for each number, we got to be smart about it. We got to ask, is this number bigger than the last number we added? Because remember, we want our combinations to be in ascending order.
Right. No going backwards.
Exactly. And then the second check, the crucial one, if we add this number to our current sum, are we going to go over n?
So we're making sure we stay within our target sum limit.
Exactly. So if both of those checks pass, if the number is bigger than the last one and we're still under n, then we can add it to our combination and update our current sum.
Okay, so we're taking a step forward in our maze, right?
Yep. And then here's the recursion part. We call our find combinations function again, but this time we give it our updated combination, our updated sum, and the next number in the sequence as the new starting point.
Ah, so it's like we're saying, hey, let's explore this path a bit further and see where it leads us.
Exactly. Now imagine we hit a point where our sum busts through n, or we've already used up all k of our numbers. What do? We're at a dead end.
Backtrack. We got to turn around, retrace our steps.
Exactly. We remove that last number, adjust our sum back down, and basically we try a different branch in our combination tree.
So it's like if the path we're on doesn't lead to a solution, we don't just give up. we back up and try a different route. I like it.
And this whole process, this back and forth, it keeps going until we've explored every possible path. And by the end, we'll have a nice, neat list of all those valid combinations.
Okay, that makes a lot of sense. It's like a systematic search, but with the smarts to know when to turn around. Now, what about that bit manipulation approach? Can we get a glimpse of how that would work in this case?
Sure. So with bit manipulation, remember, each combination is like a code, a 9-bit sequence. So imagine we have a loop, and this loop, it's going to run through all the possible 9-bit integers, starting from 0 all the way up to 511.
511, why 511?
Good question. It's because 2 to the power of 9, which is the number of possible combinations with 9 bits, is 511. So we're basically checking every possible code.
Got it, got it. So each integer is like a different combination, a different code.
Exactly. So for each of these integers in our loop, the first thing we got to do is check how many 1 bits are there in its binary representation, right? If it's not equal to k, we know it's a no-go. We just skip it and move on to the next one.
Okay, so that's our first filter, eliminating all the combinations that don't have the right number of numbers.
Right, but if it does have k1 bits, then we got to get down to business and calculate the sum of those numbers represented by those 1 bits.
Okay, so how do we actually do that sum calculation using bit manipulation?
Well, there are some nifty bitwise operations we can use. It's kind of like we're using a special mask to isolate each 1 bit and figure out its position.
A mask, like a Halloween mask?
Well, not quite, but I like the way you think. So imagine this mask, right? It's also a binary number, but it only has one bit, and we kind of slide this mask along our combination code, comparing it bit by bit.
So we're like checking each position to see if it has a 1 or a 0.
Exactly. And we can use a bitwise AND operation to do this check. If the result of that AND is not 0, then we know, boom, that bit in our combination is a 1, and we add its corresponding number to our sum.
Oh, that's pretty cool. So we're using those bitwise operations to pinpoint exactly which numbers are included in our combination.
Precisely. And once we have that sum, we just got to check. Does it match our target sum?
Right.
If it does, we've got ourselves a winner.
We add it to our list of solutions and move on to the next integer.
You got it. It's really elegant how bit manipulation kind of leverages the way computers think, at that binary level to create this really streamlined and efficient solution.
It's like speaking the computer's language, right? I'm really starting to appreciate how these two approaches, backtracking and bit manipulation, they're both so different, yet they can both solve the same problem.
It's like having different tools in your toolbox, and the more tools you have, the better equipped you are to tackle any coding challenge that comes your way.
It's fascinating how a problem that seems, kind of simple on the surface, like this combination sum 3, can have so many different solutions, each with its own, quirks and cleverness.
Yeah, it's like it really shows you the beauty of, algorithm design, right? Like having this whole toolbox full of different techniques, and each one's kind of perfect for a specific situation.
Totally. And knowing which tool to grab and, how to use it, how to adapt it, that's what really makes a programmer stand out.
Couldn't agree more. It's not just about memorizing algorithms. It's about really understanding how they work, the ideas behind them, so you can tweak them and use them for new problems.
Speaks of new problems, what if we took this combination sum 30 thing and we spiced it up a bit? What if we added a little extra challenge?
Okay, game on. What do you have in mind?
Okay, so what if, in addition to finding those combinations that add up to n, we also said those numbers got to be consecutive?
Okay, consecutive numbers. So now we're not just worried about the sum. We got to pay attention to the order, too.
Exactly. So, for example, if k was 3 and n was 12, the combination 3, 4, 5, that would be a winner, right?
Yeah.
Because they're consecutive and add up to 12.
Yep, that works.
But if we had 1, 2, 9, even though those add up to 12, they're not consecutive, so that's a no-go.
Right, got to be in order. So how would we handle that with our backtracking approach? We need to start from scratch.
Well, I think the core idea of backtracking, that whole maze analogy, it still works. We'd still be building our combinations one number at a time, backtracking when we hit a wall.
Yeah.
But we just need to add in a little extra check to make sure we're only picking consecutive numbers.
I see. So instead of looping through all the numbers from our starting point to 9, we kind of narrow it down.
Exactly. So, if our last number was 5, our loop would only consider 6, then 7, then 8, and so on.
So it automatically keeps us on that consecutive path. Smart.
And then the rest of our backtracking logic, like checking the sum and backtracking when needed, that all stays pretty much the same.
It's a great example of how we can take an existing algorithm and Just tweak it, adapt it to handle a new rule without having to, like, reinvent the wheel.
Totally. Now, I'm curious, could we pull off the same kind of tweak with bit manipulation? Can we make it work with this consecutive rule?
That's a tougher one. Remember, with bit manipulation, we're all about those bit masks, right? Each combination is represented by that pattern of ones and zeros.
Right, like a secret code.
Exactly. So to enforce this whole consecutive thing, we need to find a way to quickly look at a bit mask and know, hey, does this represent a consecutive sequence of numbers?
Yeah, I could see how that would be tricky. It's not like the ones and zeros just jump out and tell you, hey, we're consecutive.
We'd probably need to do some clever analysis of those bit patterns, looking for those consecutive ones. But hey, that's part of what makes algorithm design so fun, right? Figuring out these creative solutions even when it seems tough at first.
Totally. It's like solving a puzzle within a puzzle.
It reminds us that coding isn't just about writing code, it's about thinking differently, Thinking critically, thinking creatively to find these elegant solutions.
Well said. And sometimes the best solution, it might not be the most obvious one, right? It takes some experimenting, some playing around to find that perfect approach.
Couldn't agree more. It's all part of the journey.
This whole deep dive into combination sum 3, it's been awesome. We started with just understanding the problem, then we explored all these different ways to solve it, like backtracking and bit manipulation. We even figured out how to tweak those solutions to handle new challenges.
Yeah, it's been a great exploration of algorithms and like the whole world of computational thinking.
And hopefully, our listeners out there, they're feeling a little bit more confident, a little bit more inspired to tackle their own coding challenges.
Definitely. Just remember, keep practicing, keep exploring, and most importantly, keep that coding spirit burning bright.
And hey, don't forget to join us for our next deep dive here on AI.Code.Cast, where we'll be, breaking down more complex stuff and making it fun and easy to understand. See ya then.